Good morning, everybody. Today's topic is nitrification, denitrification. Actually, that is this week's topic. So let's first start by trying to define what we mean by nitrification, denitrification. The short version is we have NH4 that is nitrified first to NO2 by some microorganisms. Then they can go to NO3. So this part is nitrification. But then if we also want, you see when we do this, we still have just as much nitrogen in the water as we had when we started. So if we also want to remove the nitrogen, then we also have to denitrify. So then the next step is another set of biological reactions going to NO2, going to NO, going to N2O, and then finally N2, which is the most common gas in the atmosphere, so then it's released to the atmosphere, where the nitrogen originally came from. So this second part then is the denitrification. These reactions, these processes can be carried out in many different ways. And that's what we'll talk about today and tomorrow. Today we'll concentrate on the nitrification part. Right? So if we start there and we start looking for the reactions that will do this, and in general when we're looking for reactions, what table in the book do we consult? There's a table that shows all possible reactions that can happen in our water processes. And which table is that? Table 7.6. So why don't you look that up? It's on page 580 in the new book. And if you don't have a book, sit next to somebody who does, so we can work on this. So what this table gives us is half reactions. And what are the half reactions we're looking for when we look for nitrification? Just look at the table and see if you find something that we can use. And we always have to have two reactions, electron donor, electron acceptor. So which ones are valid for when we talk about nitrification? There's actually a few options here.
First one. Third.
Okay, number 3.
5.
Number 5 is a suggestion, but both of these end up with nitrogen, so that's part of the denitrification. Now let's just focus on nitrification. Now the first two reactions are just how it's used as a source when you build biomass. So what we're looking for now is just electron acceptor and electron donor. And all the acceptor equations are 3 to 8 and donor are 9 to 29. 21 is one option, and 22 is mentioned, that's part of it, yes, and 23. So it depends somewhat on what we are after, but let's start by taking number 20, let's go for 22. Okay, so what, if we go for 22, then we say that we ignore this. We just look at the reaction from ammonia to nitrate, which is the traditional way of looking at it. That is what we call nitrification. But we know there are two steps, and we can split it up and get more accurate afterwards. But you're saying we're going for 23, was it? 22. Okay, so we go for 22, and then we look at what it says. 1, 8, NO, 3, and there are some protons involved, plus 5, 4, 8 plus E equals 1/8 NH4 plus P8 H2O. We also have a delta G value, which is something we should consider, and the delta G here is 34.5. So delta G 34.5. So we say that is the reaction for the electron donor for nitrification. Then the next question is, what can work as electron acceptor for this reaction? Well, first of all, as you notice, it's written kind of the opposite direction as what we expect. This is our reactant, this is the product, and then there is an electron being released, and that has to go somewhere, so we need an electron acceptor also. And what is the electron acceptor? Which number between 3 and 8 in the table describes an appropriate electron acceptor?
1, 4, 3.
4, 6, and 7.
Many good suggestions, only one of them are right. And it's not obvious if you don't know it. It's number 4, oxygen. Oxygen is the preferred electron acceptor. It may even be the only one. So nitrification, it's a rather sensitive reaction, as we will discuss later. So if we say it's number 4, okay, this was 22, and then we have number 4 there, and number 4 says 1/4 oxygen plus proton plus electron equal to 1/2 H2O. And we have a delta G of 78.14. Actually, both of these should be minus, right? So will this reaction go? Well, obviously, if not, we wouldn't have a lecture on it, but how can we check that this reaction will actually occur? What's the requirement? Delta G must be negative, right? So delta G must be negative. The question is it negative? It is. But remember now, this one is going that way.
Plus 34 minus.
So that's actually plus 34.5, but still, the sum is negative. So yes, it will go. And if we add these two up then, do the right order, what will it look like? We have 1A NH4 plus 3A H2O plus 1/4 oxygen plus H plus minus. This must then equal 1A NO3 plus 5/4 H plus E plus 1/2 H2O. And the delta G is 40 minus 44.0. So it should run just like this equation. Of course, now we can simplify a bit. We have electrons on both sides. We can remove those. We can merge a few things, and in the end, we end up with 1A NH4 plus 1/4 oxygen equal to 1A NO3, and then we have some we have a little surplus of protons, so we have plus 1/4 H plus, right? 5/4 plus 1 or minus 1, so then we have 1/4, and we have how much water?
1/8.
Okay, is that complete? Do we have everything now? I think so. So that's nitrification. So we see that to nitrify, we consume oxygen. So it's an aerobic process. This equation with the delta G express how much energy they get for all their purposes when they nitrify. And these organisms, that's what they know how to do. They are nitrifiers, they're very specialized. You also have heard a few of these classification words. They are, what kind of organisms are they? If we want to classify these organisms that do this job, what kind of organisms? Well, one way of classifying is depending on what kind of electron acceptor they're using. And what's the electron acceptor? Oxygen. And what do we call organisms that rely on oxygen? Aerobic. So these are aerobic organisms. There is another main distinction is between heterotrophic and autotrophic organisms. You heard that distinction before. And what is the difference?
The carbon.
The carbon source,
Yeah. It's organic or inorganic.
right? And what can we say about that from what we've seen here? Are they autotrophs or heterotrophs? You cannot really see it directly, but indirectly we know that they are autotrophs. Because the heterotrophs, they get their carbon and energy from organic matter. But here we can see the energy comes from an inorganic substance. So that means they have to get their carbon from somewhere else. And where do they get their carbon from? CO2, I mean inorganic carbon. And so if you look at the first reactions 1 and 2, reactions for bacterial cell synthesis, you see that they can use CO2. So that's what they do. But because they use CO2 and the delta G is fairly low, that means these nitrifiers, they grow quite slow. At least you can look at it that way. They have to build everything from the basic building blocks, inorganic matter. So this small piece of energy they get, they have to use that to put together CO2 and build organic molecules and then build themselves. So it's a pretty rough life. They don't have much excess. So that's part of what we look at when we get into the more practical aspects is, since they grow real slow, they have to be treated nicely for us to be able to maintain nitrification. Okay, so that's basically the stoichiometry. But just for the record, if we said instead, which would be more correct, that we wanted to look at first this reaction, ammonia oxidation, and if you look in the chapter, you will see there's a special section about AOB kinetics, for example. That means ammonia oxidizing organisms. So that's one group of nitrifiers, and the next group is here for nitrite oxidation. If we were to split them up, the stoichiometry which we worked on so far, which equations in table 7.6 would we use? So if we went through this, instead of just saying there is one equation for nitrification, there is really two equations, and they are different organisms. What would be the electron? It's the same electron acceptor in both cases, or in all three cases. But what is the electron donor equations if we were to do these separate? Yeah, right. So 23 is this one. And 21 is this one. So sometimes it's necessary to do it, to split them up. And I'll just explain a couple of examples, but we'll stick to the more simple nitrification for a while, but just to explain why it can be useful to split it up. There are, for instance, some ways that you can say you only want this part to happen. You don't want to spend oxygen on this step. Because really, when you go to denitrify, you're taking this back to this again anyway. So this nitrate is kind of a dead end. So really, in some of the high-tech, high rate reactions, we kind of skip that and try to go this way. So we kind of denitrify directly from this step. It can be, there are a couple of ways we can do that. So we can call it the shortcut. So essentially then we go not that way, but we go from there to there. And then on to nitrogen. And as you see, that would save us some oxygen, and oxygen is something we want to save. Why? Why do we don't want to spend more oxygen than we have to? Oxygen is free, it's everywhere. Why don't we want to use more than we have to?
We need more time.
Not so much time as energy or money. Because this oxygen that is in the air, you need to bring it into the reactor using blowers, using electricity. So it's a waste of energy and therefore waste of resources and money. So that's why some of the new development in all kinds of treatment processes are ways to reduce the energy demand. Okay, so then we have the basic stoichiometry. Next step, kinetics. What kind of reaction rates do we get here? Right, let's do that over there. So I'll just move the camera. So, nitrification kinetics. How do we expect it to be? If we just go for our standard expression, mu, growth rate, the growth rate of the nitrifiers, what's our standard way of expressing growth rate? Some Monod equation, yes. And what are the symbols we use? What's the first thing we put up? Mu max. And what does it depend on? Concentration of substrate. Right, so we can say Cn for simplicity for ammonia, Kn plus Cn. That is one substrate, or that is kind of that's the electron donor. The thing is though, the reaction also depends on the electron acceptor. So that can then be expressed by saying this is one saturation function, the other one is similarly for oxygen. And what we know is that nitrification has a pretty strong dependency on oxygen. It says in the book that you can get increased nitrification up to concentration of 4 milligrams per liter. 4 milligrams oxygen per liter. Now what does that tell us about this KO2, the half saturation? What kind of value should this have then? I want the number. Okay, now then let's just go back to the definition. We have rate, and we have the saturation function, and we have mu max, and the book says mu max occur when oxygen is above 4. So if we then go back in here, halfway, half saturation coefficient, and this is then typically around 2 milligrams oxygen per liter. So that's how we can, just based on some words in the book, we can estimate roughly what this K value should be. And that's typically what is being used in modeling. Then we have some value for this, which we can find in a table in the book. Mu max, as I said, it's quite low compared to all the other organisms, not all, but many of the other organisms we're dealing with. Some of the anaerobic organisms are also quite low. So then we have stoichiometry and kinetics. And we can start modeling. So that's, I think, what we should do. Let's just make a very basic, simple model in AquaSim.